Okay, so let's get started. Okay, so in this lecture, we continue to talk about the process of translating a conceptual model. So in this course, we talk about entity relationship diagram, right, to a relational model, right? So essentially, we want to take as input a diagram that you can see on the left-hand side and translate that into a database schema, right? So which contains a set of relations, and each relations contains a set of attributes. So the thing that we want to understand is really when you have a conceptual model about the application that you want to build, there's often different ways that you can design the relational schema. So for example, if you give me this entity relationship diagram, right? So I could have maybe two different designs concerning the relation that corresponding to the working relationship and also the department entity set. I could have them as two separate relations, or I could merge them, right? So this is just a very simple example. In real world applications, you could have so many different ways you can design your relational schema given your application. The thing we really want to understand is really precisely how can we reason about different designs and how can we pick one that performs well for your application and what is the principle behind it. So this is what we call the database design theory. The goal is really try to understand what is a good database design and also how to formally model and enforce the property we want in a good design. So if you think about this goal, we actually decompose it into two different questions. So the first question is, we need a precise way to describe the property of your data, right? Otherwise, I have no way to reason about what is a good design, right? I need to be able to have some property of the data and being able to precisely describe that. In the last lecture, we talked about one notion of that, and that is by using functional dependency as a precise way to describe data redundancy. And the second question is, given the property of your data, in our context today, we are given all the functional dependency that you have in your application. How can we describe the property of a given database design? And that is something we are going to talk about today, and that is something we call the normal form. So before we talk about normal form, let's try to recap a little bit and think about functional dependency to refresh our memory. Right? What is functional dependency? Right? So I'm giving a relation schema R. Right? Here, for example, we have 4 attributes in this relation, A, B, C, and D. Each one has a domain, DA, DB, DC, DD. And the instance of this relation will be a subset of the cross product among all the domains. And functional dependency describes the relationships between two subsets of attributes. So here, for example, we have a subset of attributes alpha, we have another subset of attributes beta. And we say there's a functional dependency from alpha to beta. I'll say beta is functionally dependent on alpha, if and only if you give me arbitrarily 2 tuples in R, if they matches on alpha, then that implies they also match on beta, right? Which means that if you give for any relation instance, if you have the functional dependency from alpha to beta, it means that if I know the value of alpha, that will decide the value on beta. It is not possible for you to find 2 tuples that have the same alpha value, but have a different beta value. That is essentially what we want to describe by functional dependency. So if there's a functional dependency from alpha to beta, then intuitively there's a function mapping that actually maps a value in column alpha to values in column beta. And we will write it in this way, right, to really represent that the relation instance R satisfies this functional dependency. So this is just one example, right? So take as example this relation R with 4 attributes A, B, C, and D, right? So it's clear to see this instance satisfies functional dependency from A to B, right? Why? You look at every single value of A, right? So for example, for these two tuples, both two tuples have the same value on A, that is A1, but they also map to the same value of B, which is B1. You cannot find two tuples that matches on A, but have different value in B, right? So essentially, you have the functional dependency from A to B for this relation instance. So similarly, you have the functional dependency from CD to B, right? So to reason about this, we follow the same principle. I cannot find two tuples that share the value on C and D, but give me a different value on B, right? So, and similarly, right? So if you look at the functional dependency from B to C, right? Clearly, I mean, we cannot have that because if you look at the last two tuples, they share the same value on B, but they have different C value, right? So this is just one example about functional dependency. We also talk about how to reason about functional dependencies. Specifically, if you give me a set of functional dependencies, how can I reason about other functional dependencies that can be implied from this input set of functional dependencies? We talk about three reasoning rules, right? Reflexivity, augmentation, and transitivity. What's amazing about this is if you apply these three inference rules or axioms again, and again, you will have a reasoning system that is both complete and sound. By sound, we mean that if you follow these three different rules, you will always get a functional dependency that is actually correct, okay? On the other hand, by being complete, we mean that all the functional dependencies that are correct can be derived from applying these three different rules again, and again, okay? So this is just a quick kind of refresh our memory about functional dependency. In this lecture, we are going to talk about normal form, okay? We are going to go through essentially 5 different normal forms and try to reason about their property. So what is normal form? So database normalization, right, is a process of structuring a relational database in accordance to a series of so-called normal forms in order to reduce data redundancy and improve data integrity. So more specifically, normal forms is essentially a whole bunch of common ways for you to normalize your database. And more precisely, for each normal form, we essentially consider the following 3 problems. So the first one is if you give me a relational schema R, and if you give me a whole bunch of functional dependencies, FD, that this database satisfy, we want to understand how to decide whether this schema together with this function, this set of functional dependency satisfy a given normal form. Okay, so for any normal form, this is the first question we want to understand. How can we test whether your database R and FD together, and it's always a pair, satisfy this normal form? It's always question number 1. So question number 2 is if you give me a relational schema R and a set of functional dependency FD that satisfy a given normal form, what are the set of properties that it will have? Okay, so for example, whether it has update anomalies, whether it has insert anomalies, right? So if you normalize your database in this way, like what property can we say about that? So third question is, if you give me a relational schema R and if you give me a functional dependency FD, how to generate a new schema R prime such that if you take R prime and FD, they satisfy a given normal form. Okay, so for each of the normal form, we cares about these 3 different questions. So let's look at one concrete example, okay, and then it will become clear. So before we go through all the normal forms in this lecture, one thing to keep in mind is that what we are going to see today often give you a reasonable guideline about how to design your database, given the property you want from the design. However, right, so being normal is not always good, right? So when you are really designing a database in real world, sometimes you might want to be a little bit flexible compared with what we are going to learn today, okay? to design a real-world database application is always more complex than just normalize everything you have into a certain normal form. Okay, when I really do the real thing, you need to consider the properties and the performance trade-off in your application. The goal of this lecture is not give you a whole lot of rule of thumbs such that you can always apply some normal form to your application and then you're done. The goal of this lecture is really to teach you the way of thinking about normalization. And when you really apply that to real world, you kind of need to be really careful about the performance and the correctness guarantee you want in that application. Okay, just keep that in mind. Okay, so let's talk about the first normal form, which is kind of the easy one. But after you look at that, you can get a feeling about what is normal form. Okay, so the first normal form requires you to only have atomic domains. Okay, what do we mean by that? It means that every single cell in your instance need to be a value, a single value, atomic value that cannot be decomposed. Okay, so for example, this is one relational design that satisfies the first normal form. As you can see, it's a relation schema with 3 attributes, right? And every single attribute take a value corresponding to a person. Okay. So what are the design that doesn't satisfy this first normal form? So this is one example, right? If I design my database schema in this way, that I have a relation R with 3 different attributes, the first 2 attributes, father and mother, correspond take a value in a domain corresponding to a person, but the third attribute, children, take value in a domain corresponding to a set of people. If I design my database in this way, this will actually not satisfy the first normal form. When we say a schema satisfies the first normal form or in the first normal form, we mean that in that relational design, all the attributes can only take atomic value. You cannot decompose it into multiple smaller values as, for example, a set or list or yeah, something like that. So it's very simple, right? So, but to understand the first question of a normal form, given relational schema, how can we say whether it satisfies certain normal form or not, right? Here, you have a precise way. You look at every single attribute, and if every single attribute can only take atomic value, then this relational design is in first normal form, okay? So the intuition of this is, if you have this, it really makes the concept of key easier to define, right? If you think about the second example, right? So what is really a key in this design, right? And you could define it, but that is often a little bit tricky to do. So that's actually the property that one property you get from first normal form, right? So in SQL 3, and if you are doing XML, right? So often they allow you to have non-first normal form design, right? For example, you can have set, you can have list, right? So in those type of systems. So in this lecture, right? So we are always assume that our design is in first normal form, okay? And then we are going to build up other type of normal forms over this. So once your relational design is in first normal form, let's look at another normal form that is something we call the second normal form. So here's one motivating example here. Assuming I have 2 pieces of information in my application, I have a whole bunch of students, and I also know which student take which lecture, okay? How can I design my schema? Well, I could store them separately. I can have one table for students. I have one table for a student attend the lecture, right? But on the other hand, I could also have a design that I combine all the information together, which gave you a relation look like this. The first column is student ID. The second column is the lecture that student take. The third column is the name of student. The fourth column is the semester of the student. So what is the key of this relation, right? So here, because one student can take multiple lectures, so the key is a combination of the student ID and the lecture number, essentially the first 2 columns. That is the key of this relation. So what's the problem of this? The problem of this design is there are redundancy of information, right? So let's take one student, for example, the student 28106, who took 4 lectures, as you can see here. Because these students, like the name of students is independent from the lectures that the student took. Need to store the information of the name of the students and also the semester multiple times, right? How many times do I need to store them? That's actually equals to how many lectures that student take. So this is one type of data redundancy that you can see from this design. So essentially for each student, the name of students and the semester of students is stored multiple times. And in applications that could cause problems, right? So if you think about why that could happen, it's essentially fundamentally speaking, right? So you have the key of the relation, which is a combination of the student ID and the lecture number. Essentially, you have the functional dependency from the ID and the number to the name and the semester. But on the other hand, you also know the name and semester of the student is functional dependent on the ID itself, not on the lecture, right? So you have another functional dependency from ID to name and semester. The reason you have redundancy in this design is you have these 2 functional dependencies in your application. You have one functional dependency, map leggy and number to name and semester, and you have another functional dependency, map from leggy to name and semester. And because leggy is a subset of the key, you have redundancy. Okay, so that's actually something you can see here. I mean, the key here is leggy and the number, but given the leggy, I also know the name and semester already, right? So if you because the key is a combination of the first 2 attributes, I will have redundancy, the duplicates in the first attributes. And whenever you have duplicate here, and because I have a functional dependency mapping leggy to name, I'm going to have redundancy on name. That's a fundamental reason that why we have this type of redundancy in this design. So second normal form try to remove data redundancy caused by this. And we say relational design is in second normal form if and only if every non-key attribute is minimally dependent on a key. So what do we mean by that? By minimally dependent, we mean that there's no attribute depends on part of the key. Okay, so more concretely, if you look at this example, this functional dependency, leggy and name to name and semester, is the reason that this design is not in second normal form. Why? Because if you take a kind of non-key attributes, here's the name, that actually depends on leggy, which is part of a key, right? Essentially, you have functional dependency where the left-hand side is only a subset of a key. If that happens, then this design is not in second normal form. So the problem for relation that's not in second normal form is that it could have a whole bunch of anomalies. So for example, you can have insert anomaly in this design, right? So assuming I have students who haven't taken any lecture yet, right? If I want to insert that into the relation, essentially I don't really know what to do, right? Because my key is leggy and the lecture number. So what should I put in the second attribute, right? So I cannot put another because it's a key, right? So that could have a whole bunch of problems when you try to insert a student into this. And you have update anomaly, right? For example, you want to increase the semester number of a student by 1, right? So in this case, if you want to do that for these students who took 4 lectures, you need to do that 4 times, right? So if you are not being careful, you could have very easily have a database that is not consistent, right? Because you kind of forget about updating some of this. Right? So and also on the other hand, it could be very slow because every single update query need to touch multiple tuples in the relation. And you could have delete anomaly, right? So for example, you have one student, the first student who drop a lecture, right? So what can you do, right? So you cannot delete this tuple, right? If you delete this tuple, you are going to lose the other information. Essentially, you are removing the student from the database at all, right? So this is actually 3 different type of anomalies that could happen because this relation is not in second normal form. So how can we enforce second normal form, right? So that's the third question that we talk about for normal form. That is, if you gave me a relational design that's not in second normal form, how can we decompose it? Or how can we change it to something that's in second normal form, okay? So in this example, it's kind of pretty easy, right? You take one functional dependency that's evil. Evil means that because of that functional dependency, this relation is not in second normal form, and you decompose it, right? So in this example, you have one functional dependency that's evil, which is from Leggy to name and semester. To enforce second normal form, you just take that functional dependency and you create a new relation, okay? With only Leggy, name, and semester, and you have another relation with the rest of attributes. In this example, it's a Leggy and lecture number, okay? By decomposing this relation, the students attend relation, into 2 relations, one for students, one for attendance, you can actually enforce second normal form for this application in each of this relation. If you look at students, right, Leggy is a key, and it's only have one functional dependency from Leggy to name, Leggy to semester, right? So you do not have a non-key attribute, name or semester, that depends on a subset of a key. So students is in second normal form. Similar for attendance, right? So it only have 2 attributes. The combination is a key, right? So essentially the attendance is also in second normal form. This is a precise systematic process that take as input a relation that's not in second normal form and turn that into a set of relations, each of which is in second normal form. And it's very easy to see that this decomposition is also lossless. And we talk about how to test that in the last semester. Sorry, like in the last lecture. Okay, so this is about second normal form. One thing that we want to think about, now we know what is second normal form and how to decompose the relation into second normal form, is that if I have second normal form, is that enough, right? So that second normal form gets rid of all the anomalies that like in my data. If I have a relational design that's already in second normal form, that can it still have insert anomaly, update anomaly, and delete anomaly? To answer that question, let's look at one example. So I have a relation with 4 attributes, A, B, C, and D, and I have 2 functional dependencies here. I have one FD from AB to CD, which essentially means that in this example, AB is the key, okay? And I have another functional dependency from C to D. That's this relation in satisfy second normal form. So let's think about this. To test whether this relation is in second normal form, we have a very precise process. Essentially, you look at every single attribute. You look at A and you think, is A a key? Is A part of a key? Yeah, in this case it is, because AB is a key, right? So then I'm fine. And look at B, is B part of a key? Yes. If you look at C, C is a non-key attribute in the sense that C is not part of a key, right? And then you look at whether C functional depends on part of a key, right? So in this case, that's not the case because C only depends on the combination of A and B, which is a key, that's fine. And if you look at D, right? So like in this case, that's D kind of depends on part of the key, right? So that's also like not the case here, right? So essentially for this relation, it's actually in second normal form. But as you can see, for this relation, it could also have redundancies in the data. Why? Because if you look at the column C and D, right? So whenever you have one value of C, it can actually decide the value of D. So in this case, if I have two tuples with the same value of C, I'm going to store the same value of D multiple times, right? So that's another kind of type of data redundancy in this relation. And because of that, you could have a whole bunch of anomalies. You can have updated anomaly, you can have delete anomaly, right? Because of that data redundancy. But on the other hand, this relation is actually in second normal form. So why? The reason is that you have one functional dependency from C to D that's actually evil, that's actually cause this type of data redundancy. But our definition of second normal form is not strong enough to eliminate this type of data redundancies. So what should we do, right? So one thing we could do is let's define a stronger notion of normal form, and that gave us something we call the third normal form. Let's look at definition first. So we say relational design R is in a third normal form if and only if for all functional dependencies from alpha to B, alpha is a subset of attributes, B is a single column, at least one of the following three conditions hold. First, either this functional dependency is trivial, and we talk about what do we mean by that. Essentially, we mean that the right-hand side is a subset of the left-hand side. Either this functional dependency from F to B is trivial, or B is an attribute of at least one key, okay? Or the third condition is alpha is a superset of a key, or super key, okay? If for all functional dependencies that you have, they satisfy one of these three conditions, then we say this relation R is in third normal form. So why do we define this, right? So intuitively, right? So if you have a functional dependency from F to B that does not satisfy any of these conditions, right? So essentially, intuitively, you have two concepts in the same relation, and one concept corresponding to alpha and another concept corresponding to B. In that case, it's better to actually decompose them into different relations, one contains information about alpha, another contains information about B. Okay, so that's intuition of third normal form. And another intuition is that we try to get rid of the transitive dependency. For example, I have three attributes. There's a FD from A to B, there's a FD from B to C. This type of transitive dependency is okay for second normal form. But if you actually apply third normal form here, you can see whenever I have this type of transitive dependency, they will not be in third normal form, okay? Let's go back to our example here. So as we can see for this example, this is actually not in third normal form. And the reason is you look at the functional dependency from C to D. Let's check each of these conditions. First one is C to D trivial. It's not trivial because the right-hand side is not a subset of the left-hand side. And second is the right-hand side an attribute of at least a key. So in this case, no, right? So because only AB is key. And the third one is whether the left-hand side, in this case C, is a super key, right? In this case, that's also not the case. So because of the functional dependency C to D, this design is not in third normal form. And that is why we have a data dependency in this design. So another question that we want to understand is once we have a relation in third normal form, does it get rid of all the data redundancies? So it's actually no. To understand why, let's look at this example. So we have 4 attributes in this example, and we have 2 functional dependencies. We have 1 functional dependency from ABC to D, and we have another functional dependency from D to C. So let's first think about whether this design is in third normal form. In this case, right, so let's check the second functional dependency. Is this trivial? It's not trivial, right? Because the right-hand side is not a subset of the left-hand side. Is the right-hand side an attribute of at least a key, right? In this case, it is, right? So the key of this relation is ABC, and you can see the right-hand side is a subset of a key, right? So essentially, this functional dependency D to C is okay for third normal form. It satisfies one of these 3 conditions. So this is a design that satisfies the third normal form. But do we have data redundancy here? Yeah, clearly we have, right? If you think about C and D column, right? So at the moment you have a same value of D, you are going to store the same value of C, right? So there are data redundancies in this relation. It could have update anomaly, it could have delete anomaly, right? So because of that redundancy. So essentially, even though the third normal form is stronger than second normal form in the sense that it can get rid of more type of data redundancies, it still could have data redundancies. It's still not strong enough. Okay, in this example, it could allow a functional dependency from D to C. So what can we do, right? So yeah, we can keep making this stronger, right? So another stronger notion of normal form is something that we call BCNF. Okay, so here's the definition. We say a relation R is in BCNF if and only if for all functional dependencies that you have from alpha to B, at least one of the following 2 conditions holds. Either the functional dependency is trivial, that is, the right-hand side is a subset of the left-hand side, or the left-hand side is a super key, that is a superset of some keys. Essentially, compared with third normal form, we cannot get rid of the second condition. And if for all the functional dependencies in your system, it satisfies one of these 2 conditions, then we say that relation design is in BCNF. Intuitively, right? So if you think about this, whenever a relation design is in BCNF, for every single relation, you kind of store essentially the same information once, right? So if you look at both of the conditions, right, both of them are kind of trivial, right? So and that is actually essentially you don't have those really non-trivial functional dependencies in every single relation. That is intuitively what we want to enforce in BCNF. So let's look at one example. Okay, so we have a relation with 4 attributes A, B, C, D, and we have that ABC decide D, right? It should pretty much like ABC is a key, and also AD is a key. Okay, AD decide BC. Okay, and then we have there's a functional dependency from D to C. So if you look at this thing is actually in third normal form. Why? Well, we just need to check every single functional dependency, right? So for the second one, BC, the right-hand side, is a subset of a key, right? Then it's fine. For the third one, the right-hand side is a subset of key, right? So essentially, this design is in third normal form. But on the other hand, it's actually not in BCNF. If you think about why, just look at the functional dependency from D to C. First one is a trivial. Well, it's not trivial. It's like the right-hand side is not a subset of the left-hand side. And second is the left-hand side super key. Right? In this case, no, right? So there are only 2 keys, ABC and AD. D is not a superset for any of those. So essentially, because of the functional dependency from D to C, this design is not in BCNF. but it is in the third normal form. Okay. Now we talk about the third normal form. We talk about the BCNF, right? So there are multiple questions that we are curious about. The first question is, if you give me a database schema, how can we turn that into something that satisfies BCNF? And question number 2 is, if you give me a database schema, how can we turn that into something satisfy the third normal form? And the third question is, why do we talk about both, right? Why don't we just talk about the strongest one, right? Why don't the whole lecture be about BCNF, right? So there's a trade-off between the third normal form and the BCNF, and that is something we are going to talk about as our third question. Okay, so now let's look at each of these questions one by one. So the first question is, if you give me a relational design R that's not in BCNF, how can we have an algorithm that decomposes R into a set of smaller relations, R1 to Rn, such that it satisfies two conditions? First one, R1 to Rn is a lossless decomposition of R, meaning that if I join them together, I will perfectly recover all the information in R. And second, I want each of Ri satisfy BCNF. So that's the algorithm that I want. To do this, there's actually a very simple systematic algorithm to achieve that. So it works as the following. You start from a single relation, R, and then you look at whether every single relation in the result set is in BCNF. If you can find one relation in the result set, and to start, we only have a single relation here, that's not in BCNF, it means that you must be able to find one functional dependency here from alpha to beta that's evil. Evil means that because of that functional dependency, this relation Ri is not in BCNF. And you take that functional dependency, you decompose Ri into two even smaller relations. The first relation, Ri1, contains the attribute which is the union of alpha and beta, both the right-hand side and left-hand side. And you have a second relation, Ri2, contains like all the attributes in Ri except those in beta. You have Ri minus beta as the second relation. And then you put Ri1 and Ri2 in your result set, and you remove Ri from your result set, right? Essentially, you kind of decompose Ri into two even smaller ones. And you keep doing this until all the relations in your result set are in BCNF, okay? And then you output the result, and that's your decomposition. As long as you can find some relation in the result set that's not in BCNF, you must be able to find some functional dependency that's the reason, and then you use that functional dependency to decompose that relation into two smaller ones. If you follow this algorithm, you are going to have a lossless decomposition of your input relation, and each of those smaller relations in the decomposition is going to be in BCNF. So let's look at one example here. If you give me a relational design like this, you have ABC, you have three functional dependencies here. You have ABC to D, AD to BC, and D to C. In this case, we need to check whether this relation is in BCNF. In this case, it's not. Why? Because of the third functional dependency from D to C. What should we do? We take that functional dependency, we decompose this relation into two smaller relations. One contains both the left-hand side and the right-hand side of the evil functional dependency. Here you have one relation with C and D, and you have another relation that contains ABD. Okay. And if you look at this gives you a lossless decomposition of the original relation, meaning that if I join both relations, I will recover perfectly all the information in my input. And second, if you look at each of them, I think in this example, they will already be in BCNF. Okay, so this is just one example of one step in the algorithm. And you keep doing this for every single small relation. You keep decompose them if they are not in BCNF. And once you cannot decompose any of them anymore, you are done. Okay, so that's the algorithm. So there are multiple statements we can make for this algorithm. So the first one is, can we prove it is correct, right? Can we prove it's really gave us that input and output property that we want? So statement number one is, okay, so each of this R1 to Rn as in the result of this algorithm will be in BCNF. In this case, the proof is kind of trivial almost by definition, right? So if I cannot, like if one of the Ri is not in BCNF, the algorithm will not terminate, right? So, and second statement is this R1 to Rn is a lossless decomposition of R, right? So here you kind of prove by induction, right? So essentially, like assuming you are at step n-1, and you'll say, okay, so for one relation after this decomposition, I have a lossless decomposition of that specific relation, small relation, and you do that by induction, right? So essentially that is how prove it. And the third statement is the algorithm always terminates. So how to prove that? Well, so you kind of count the number of evil functional dependencies, right? So the high level intuition is after one decomposition, you will get rid of at least one evil functional dependencies. And because the total number of evil functional dependencies are finite, you can only do finite amount of decompositions until the algorithm terminates, right? So, and that is why the algorithm will actually always terminate. You put together all the three statements, each of them are actually easy to prove, you get the proof of the correctness of this algorithm, okay? So now let's look at one example. So assuming we have a professor relation look like this, which is a very large relation. You have the personnel number, you have the name, level, room, and the address, the city, street, zip code, area code, canton population, okay? Assuming this is a very large relation that we call professor. And there's a whole bunch of functional dependencies here. So first one, if I know the personnel number of the professor, I know the name, I know the level, I know the room, I know city, street, content, etc. I know everything related to that professor. Okay, this is the one functional dependency. And second functional dependency in our system is once you know the room, you know the person. Okay. Once you know the street, the content, the city, you know the zip code. Once you know the city and the content, you know the population of the content, you know the area code. Sorry, you know the population of the city. Okay, and you know the area code. Once you know the zip code, you know content city. Okay, so let's assume this is the 5 functional dependencies we have in our system. So let's think about 3 questions. Actually, 2 questions, sorry. One question is whether this relational design, given these 5 functional dependencies, are in BCNF. And second is if it's not in BCNF, how can we decompose it? So that's the 2 questions we are curious about. So now let's take a break, and in 15 minutes, let's go through these applications. Sorry, let's go through these examples. Okay, yeah. And if you have any questions, just speak up. I will answer them. Yeah.
Hello.
Hello. Yeah. Go ahead.
There was some confusion in the chat.
Yeah.
Where you at one point, I think if you go there were 2 relations, like the one before and the one before that, where I think we had 3 functional dependencies.
Yeah,
and
let me go back to the.
Sure.
So sorry, in this one.
Yeah, the one before. The one before just didn't have the last FD, like D to C, I think.
The one before this one?
Exactly.
Okay.
And someone asked why D alone cannot be a key. And
so okay, so what's the question? Why D is not a key?
Yes. No, yeah, why D cannot be a key from this one? That was the first question.
Why D cannot be a key from this one? Okay, okay. So given these two functional dependencies, you cannot prove D is a key, right?
Sure.
Yeah. So D could be a key, but you cannot prove it, right? So you can, there are relation instances where D is a key, but there are also relation instances that satisfy the two functional dependency that D is not a key. Right. So here is D is not a key of this system, right? I mean,
yes.
that's not something you can derive from these two functional dependencies.
Okay. So
right?
Sure, makes sense.
Yeah.
And wait, let me check, because there was a follow-up question to that, because I gave probably a wrong response, but I need to think about it for a second. So wait, never mind.
So for example, in this example, D is clearly not a key, right? You have like the same value of D that map to different attributes, right? So, but fundamental reason behind it is from these two functional dependency, you cannot prove there's FD from D to ABC. You cannot apply Armstrong's axiom again and again to derive that.
Oh, okay, that makes
right?
sense.
So, and another way to think about it is I calculate the closure of D. That closure is not ABC.
Sure.
Yeah.
Sure, and the follow-up, like I remember what the follow-up question was, but you just, or it got answered for me by your response. So, thank you very much.
Yeah, sure. Yeah, thank you for summarizing the question in the chat window. Yeah. Yeah, so we have one question in the chat window. How can we actually infer keys from looking at FDs, right? So for example, if you want to say, okay, so there's one systematic way to do it. In this example, you want to say, okay, I want to see whether D is a key. Okay, so what you are going to do is you are going to calculate the closure of D. Right, so we talked about in the last lecture, which is all the functional dependency D to X, right? So that you can prove from the system, right? So like, for example, you say, whether I can prove D to A, whether I can prove D to B, whether I can prove D to C, D to D, right? So whatever you can prove, you put them together, it forms the closure of attribute D. And then you check whether the that closure equals to essentially all the attributes, right? So for example, the definition of a key is if I have A, B, C, D here, if D is a key, it means that you can actually prove there's a functional dependency from D to ABC, okay? Which is equivalent to say the closure of D equals to all the attributes. If that is true, then D is a key, okay? Okay, so let's continue. Sorry. Okay, so we were talking about this example, right? So there are two questions that we want to understand. The first question is whether this design is in BCNF. And second, if it's not, how can we decompose it by applying the decomposition algorithm to turn that into something that satisfies BCNF? So let's look at the first question, right? So in this example, so clearly it is actually not in BCNF, right? So for example, like if you look at so like this functional dependency, right? So this functional dependency, pretty much there's so many different ways that you can make this not in BCNF, right? So and yeah, so we can move on to the second question, that is how can we decompose it, right? So and when you talk about decomposition algorithm, we will find one evil functional dependency that's make it not in BCNF, right? So how can we do that? So there are multiple steps. So first step is we generate the closure of all the functional dependencies, right? Pretty much we want to reason about, okay, what are all the functional dependencies that can be derived from these 5 given functional dependencies. And then we can find essentially all the candidate keys, right? So there's a very precise way to check whether one set of attributes is a candidate key. How to do that? You give that set of candidate, so you give that set of attributes, you calculate the closure of that, and then you check whether the closure equals to all the other attributes. Because the definition of candidate key, right? If the subset of alpha is a candidate key, it means that you can prove a functional dependency from alpha to all the other attributes. Okay, that's the definition of key. So in this example, right? So I think the personnel number, right? So is like it's candidate key, right? So and also the room, right? Is also a candidate key, right? So like how to do that, right? So you try to prove there's a functional dependency from personnel number to all the other attributes, right? So in this case, personnel number decide name, level, room, city, street, canton, right? So and then if you take city and canton, right, you can decide the population, area code, so on and so forth, right? If you take city, street, canton, you can decide the zip code. Pretty much as long as I know personnel number, I can decide all the other attributes. So personnel number is a key. And also if I know the room and know personnel number, right? So which also means that room itself also a key. So there are 2 candidate keys in the system. One is personnel number, another is room. And then we check each functional dependency and see like whether this one is BCNF. Okay, if it's not in BCNF, we find our evil functional dependency that we can use it to do decomposition. Okay, so in this case, right, there are so many different like functional dependencies that break that, but we can take one, which is the one from zip code to canton and city. Okay, so clearly like this one is for BCNF, you check 2 conditions, right? So first one is whether the right-hand side, sorry. So like whether this functional dependency is trivial, right? In this case, it's not trivial, right? The right-hand side is not a subset of the left-hand side. And second, whether the left-hand side, the zip code, is a super key, right? So in this case, your key is either personnel number or room, right? Zip's clearly not a superset of any of those. So this is just one evil functional dependency. So there are other evil functional dependencies. For example, if you take street, canton, city, and zip code, that's also another functional dependency. Make this relation not in BCNF. Okay, but here we found one. So then we can actually take that and decompose this relation. We will generate one relation with both the left-hand side and the right-hand side of this evil functional dependency, and that is the zip code. You have zip, you have canton, you have city. And then I have another relation with essentially the rest of the attributes and also the left-hand side. That is, I have a professor new relation with personnel number or the other. I have zip code, but no canton and city. Okay, so that is one decomposition. It is lossless because if I join them on zip code, I can recover all the information. There's no redundancy, there's no missing tuples. Why? Because of the functional dependency from zip code to content city. Okay, because of that, this is a lossless decomposition. And then we repeat this multiple steps for multiple times for each of this new relation. Now let's look at Professor New. Okay, whether this relation is in BCNF. Well, so in this case, right? So let's try to find the candidate key. So here again, the candidate key is the personnel number and room. And then let's check each functional dependency in the closure, okay, to see whether this Professor New relation is in BCNF. In this case, I can still find an evil functional dependency. So that is, if you take the one from zip code to population area code, right? So that's evil, right? So why? It's not trivial. The right-hand side is not a subset of the left-hand side. And second, the left-hand side zip code is not like a super key. Okay. So what can I do? I can take that functional dependency and then I can decompose it. Okay. So in this case, I could decompose this into two other relations. One relation contains the zip code and the associating area code and population. Okay. So and the second, I can take another relation. I can decompose into another relation with professor information and zip code. So and then I repeat this for every single new relation, right? And then I can check. So in this case, if you do this type of decomposition, I have this. I can decompose this professor relation into the three smaller relations, and you can check whether each one of them is in BCNF. In this case, they are, and then you have the result of your algorithm. Okay. So one thing that we need to be really careful about is whenever you are checking the second step, you check whether there are evil functional dependency. Whenever you are doing that, you need to check all functional dependencies in the closure instead of just what is written here. Okay, so you need to check all functional dependencies that can be derived from the set of functional dependencies that you are given in your application. Okay, that's something you need to be careful about. So another thing that's interesting about BCNF is by looking at this functional dependency. From street to content, city to zip code. So we have this functional dependency in my input, right? So that's what I have. But after the decomposition, as you can see, these functional dependencies get lost. Why? Because I can only enforce functional dependency at relation level. And these four attributes, the street, the content, the city, the zip code, they do not appear together in my decomposition. I have a relation with street and zip code. I have a relation with zip code, content, city without street, right? So there's no relation contains all four attributes, which means that after my decomposition, I cannot enforce that, right? So this functional dependency in my input gets lost during decomposition. And this is actually very interesting. That is BCNF, they do not preserve all the functional dependencies. There could be some functional dependency get lost during decomposition. On the other hand, as we will see, the third normal form will preserve all functional dependencies that we will see. Okay, so that's one kind of important difference between BCNF and the third normal form. And another thing that we want to understand is also BCNF does not get rid of all data dependent, like all data redundancies, as we will see. Okay. So it gets rid of all data redundancies caused by functional dependency. But there are other type of dependencies that not functional dependent. There are other type of redundancies that is caused by other type of dependencies. And we are going to see that at the end of this lecture. Okay. So these are the two properties of BCNF. First one, it doesn't preserve all FDs. You could lose FD during decomposition. And second, it gets rid of all redundancies caused by FD. It doesn't mean it gets rid of all redundancies, but it gets rid of all redundancies caused by functional dependency. So that's the two property of BCNF. Another thing is Because when we are doing decomposition, we are doing one evil functional dependency at a time. The order for you to pick in the evil functional dependency actually matter. For example, if you pick this functional dependency, the street content city to zip code at the first, then you are going to have a different decomposition at the end. Okay, so essentially, if you follow our algorithm, there could be multiple different ways that you can decompose an input relation into a set of smaller relations that's in BCNF. They could be different, depending on the order they'll pick your evil functional dependency. A natural question to ask is, how can we decide on the order? Right? What is a good order for you to do this decomposition? Right? So, well, I mean, that's always case by case, but there are actually some heuristics to help you to decide. So one heuristic is you prioritize the functional dependency with the largest right-hand side. Okay, so intuition, if you do that, you will have a decomposition that's roughly balanced, in the sense that you will not have a whole bunch of smaller relations. You will end up have kind of two very large relations, right? So, and then essentially, intuitively, in many cases, you will not lose that many functional dependencies, hopefully, right? So, and that's, but it's just one heuristic. It's very easy for you to construct a case that is not the best solution, but in real applications, you need to really understand the application, try different ways to decompose it, and pick the best one that makes sense, okay? But different orders of picking the evil functional dependency actually matter. Okay, so this is about BCNF. We talk about how to decompose a relational schema into a set of smaller relations, each of them satisfy BCNF. Now let's talk about the third normal form, okay? So here, let's refresh our memory. Okay, so we have relation R is in third normal form if and only if for all the functional dependency in the system from F to B, at least one of the condition hold. Either is so either it is trivial, okay, right hand side is a subset of left hand side, or the right hand side is an attribute of at least a key. Okay. Third, the left hand side is a super key. Okay. So you have one additional kind of conditions compared with BCNF. So here we try to understand how can we essentially turn a design that's not in third normal form into a design that's in third normal form. Essentially, if you give me the input R, I want to output R1 to Rn such that two condition holds. One, R1 to Rn is a lossless decomposition of R, meaning that if you join them together, you get R, perfect R, okay? You don't lose tuple, you don't have additional tuple, you just get R if you join R1 to Rn. And second, we want each Ri in R1 to Rn in third normal form. That's the algorithm we want. So here, the algorithm is also very simple. It's called synthesis algorithm. It's not decomposition because, so as you will see, the algorithm actually run bottom up instead of top down compared with the decomposition algorithm. So it's very simple. You first compute the minimal basis of F. F is all the functional dependency you have in the system. You first compute the minimal basis, right? We talked about minimal basis in the last lecture. That is actually the smallest set of functional dependencies using which you can derive all the functional dependency in F. Okay, essentially that's like the core of the functional dependencies. Okay, and then for each functional dependency, alpha to beta in the minimal basis, you create one relation that contains the attributes on both the left hand side and the right hand side. Essentially, you have alpha union beta, you create that. And if none of, and you create a one relation for each of the functional dependency in the minimal basis. If none of the above relations contains a super key, you add the relation with a key. Okay. For example, if you have k functional dependencies in your minimal basis, you either have k relations at the end, or you have k plus one relations at the end. depending on whether the K relations contains a super key or not. Okay, so and then our last step, right? You eliminate those kind of relations that is a subset of some other relations. If you have a relation R alpha at the end, you have R alpha prime. If alpha is a subset of alpha prime, you get rid of R alpha. Okay, you try to merge those relations at the end. If you follow this, you are going to have a lossless decomposition of the original relation R, and each of the relation in the decomposition are going to be in third normal form. Now let's look at one example. So take this relation on the right-hand side. I have 4 attributes. I have 2 functional dependencies. I have the one from AB to CD, which is essentially means that AB is a key. I have the one from C to D. I first calculate the basis, right? So essentially, my basis is that I have one functional dependency from AB to C. I have another one from C to D. Okay, given these 2, I can derive this like original 2 functional dependencies. This one is the minimal basis. Also, I cannot simplify this filter, right? So this is the basis. And then what I'm going to do is I'm going to take each of the functional dependency in the basis. I will create one relation for each of those functional dependency. If I take AB to C, I'm going to have one relation contains ABC, the 3 attributes. If I take C to D, I'm going to have another relation with 2 attributes, C and D. And then I'm going to check if some of this relation contains a super key. In this example, the key is AB, right? So I have one relation here, ABC, contains the key. Okay, so I'm fine. I don't need to add a relation with a key. And then I see whether I can eliminate some of the relations. In this case, this small relation C and D is not a subset of ABC. So I cannot merge them. So I'm done, right? So this is just take as input this relational design. I run my synthesizer algorithm, then I decompose it into 2 relations. One with ABC, another with CD. Okay. Now let's look at a more complex example. Let's go back to this, right? So this is the same schema as what we had before, right? You have the professor table of all those FDs. So the first step of running the synthesizer algorithm here is to generate the basis, okay? And then you generate one relation for each FD, right? So in this case, you are going to have something like this, okay? So when you go back home, you can actually write down the basis, right? And then for each of them, you can generate essentially one relation here. So here in this example, we are already pretty much half the basis here, okay? So it saves you some effort, but whenever you are dealing with some real example, you need to calculate the basis by yourself. So here, for each of this the FD here, I generate essentially one relation, and then I check whether there are some relations with a key. In this case, the candidate key is either personnel number or room, right? So I have one relation contains a key, so I'm happy. I don't need to add another like relation with a key. And then I merge them. Okay. So in this case, what do we mean by that? So if you look at the second relation, it only contains the personnel number and the room, right? In this case, it is a subset of the first relation. First relation also have personnel number and room. In this case, I will merge them and get rid of the small one. So similarly, if I look at this relation with city, zip code, and canton, right? So and look at this city, street, zip code, canton, right? So I can actually merge them, and then I'm done. I get essentially 3 relations in my decomposition. So let's look at this decomposition, right? So first one is lossless. Yes, right? So you can actually join this 3 relations together, and you get your original relation. So essentially, for all the result of the like for all possible relation instance, if you run the synthesizer algorithm, right, you are going to have a lossless decomposition. And second, that this preserve all the functional dependencies. This is very interesting because actually, yes. So for the synthesis algorithm or for third normal form, it's actually going to preserve all the dependencies. Why? Because for each of the functional dependencies in the basis, we have one relation. And whenever we merge them, we only make that larger, right? So by running synthesis algorithm, different from the decomposition algorithm in BCNF, you will never lose a functional dependency. Okay, you are going to preserve all the dependencies. That's a very good property for third normal form. On the other hand, do we have redundancies, right? So here, yes, we do have the like redundancies caused by functional dependency, right? So if you look at the relation this city, street, zip code, and canton, right? This relation is not in BCNF, right? I mean, it's in third normal form, but not in BCNF, which means that this one is going to have some data redundancy caused by functional dependency. So if you put this side by side, right? So we have third normal form and we have BCNF. If you compare them, you can see there's a trade-off. On one hand, if you do third normal form, it's going to preserve all the functional dependencies, which means that it's actually correct. Okay, you are not going to lose FDs. But on the other hand, the BCNF could lose some of the functional dependencies. But on the other hand, third normal form is going to have data redundancy caused by functional dependency, but BCNF doesn't have that. BCNF still have redundancy, but it's going to get rid of all the redundancies caused by functional dependency. So essentially, if you put them together, there's a very interesting trade-off between correctness and efficiency. And that is why in real-world applications, sometimes we need like one or the other. But as someone who use database in real world, you kind of need to know both. That's why we talk about the both in the lecture, because both of them are very interesting. If you want to emphasize correctness in your application, that is, I want to have a design that respects all of my functional dependencies, you need third normal form, because if you do BCNF, you might lose some of that. If you really want to emphasize efficiency, right? I want to get rid of data redundancy as much as possible, then maybe you need to use BCNF. Which one that you want to emphasize in your application is a property of the application. You really need to take your application and try to reason about what's important for your use case, okay? Okay. Now we talk about BCNF, right? So that is the strongest normal form that we have been seeing so far. Now let's continue our exercise to understand, is there any problems for BCNF? Do we need to make that even stronger? So now let's look at this. You have the skills table, you have the person number, right? And then you have two other attributes. You have the language that person speaks, and you have the programming language that person knows how to write. In this case, you have one person, right, who speak Greek and Latin, and who can also use C and Pascal, right? So, and then because in this application, the language that the person speak is independent to the programming language that person knows how to write in. In this example, if someone knows to speak two languages and also know how to program in two different programming languages, you are going to have 4 different tuples in this relation. However, on the other hand, this relation is actually in BCNF, right? So you can actually go through the exercise to actually check all the functional dependencies you have in this application, right? So you are going to reach the same conclusion that this relation is actually in BCNF. But clearly, there are redundancies in the data. It means that BCNF doesn't get rid of all the data redundancies. So it means that if you want to reason about data redundancy that goes beyond functional dependency, we kind of need a different notion of dependencies to really describe that. So there are multiple ways for you to get rid of redundancies here. So one way is to turn it into something that's not in the first normal form. For example, when you are using some, like for example, SQL 3 or XML, you can have a design that looks like this. You can have language as a set. You can have programming language as a set, right? If you do this, you can see there's no redundancies anymore. You could extend your notion of redundancy and dependency to non-atomic values. That is one path you can go, which is going to give you a different set of theory about how to extend our notion of functional dependency. The downside is that it's not going to be in first normal form. So what if we really want first normal form? We want every single attribute to take an atomic value. And then you need to design a different notion of dependency or redundancy to really express the information that there are some attributes that are conditionally independent to some attributes. So here, the language and programming language are conditionally independent given the person number. So that is the thing you want to express. And clearly, functional dependency doesn't give you that. So if you really want to stay in first normal form, we kind of need to define a new notion of dependency. And that gave us something that we call multi-value dependency, and gave us a new normal form associated with that we call the first normal form. Now let's talk about multi-value dependency, okay? So we have a different notation for that. There's actually two arrows here, A arrow, arrow B, right? So essentially we have a MVD, multi-value dependency from A to B, okay? So, and like you can actually write the multi-value dependency from A to C, right? Something like this. So the intuition is, if you give me a relation look like this, that is, the value of B is conditionally independent. So value of B and C are kind of independent given A, which means that for each A, I have different B. For each A, I have different C. If I have like two possible value of B for A, I have two possible value of C for A. At the end of the day, I'm going to have 2 times 2 equals 4 tuples in my relation. If that is the thing you want to kind of model, right? So we say there's actually a multi-value dependency from A to B. There's a multi-value dependency from A to C. Intuitively, that is what you are trying to kind of convey. Precisely, we say there's a multi-value dependency from alpha to beta, where alpha is a subset of attributes, beta is a subset of attributes. And we have relation schema, contains alpha, beta, and gamma, 3 disjoint set of attributes. We say there's an MAD from alpha to beta, if and only if the following is true. That is, if you give me 2 tuples, T1 and T2 in R, any 2 tuples, and they match on alpha, they have the same value on alpha. In this example, they have the same value on A, okay? That implies you can find another 2 tuples, T3 and T4, such that all these 4 tuples, T1, T2, T3, T4, they match on alpha. On the other hand, T3 matches T1's beta, and T4 matches T2's beta, and T3 matches T2's gamma, and T4 matches T1's gamma. That is, you can actually exchange it, okay, independently. If this is true for any pair of T1 and T2 in R, then we say there's a MVD from alpha to beta. Intuitively, what we are trying to say here is that if you gave me 2 tuples, T1 and T2 look like this. T1 has a value A, B, C for alpha, beta, gamma. T2 has a value A, B prime, C prime for alpha, beta, gamma. As you can see, it's color coded. I can always find T3 and T4 that swap it. Okay, so I can always have T3 and T4 that have the same A value, has the B here, and have a C prime here, have a B prime here and C here. It's just a very precise way for you to really express information that beta and gamma are conditional independent given alpha. Okay, if this is true for any pair of tuple T1 and T2, then we say there's MVD from alpha to beta. Okay, so I think someone raised hand. Yeah, go ahead. Any questions?
I have a question.
Yeah.
So this multi-value dependency, does this only, you cannot judge whether or not, you cannot about a general relation, you cannot say whether or not there's multi-value dependency. So for example, if you know like this relation has alpha, beta, and gamma, you cannot automatically say that there's a multi-value dependency because you don't, because if it only has one row, let's say if it only has row T1, then you cannot find another row for which this is true as well. Do you understand what I mean?
I understand what you mean. I understand. So essentially what you mean is that what if I have a relation with only one tuple, how can I even check it?
Yes.
So here, T1 and T2 can be the same tuple.
Oh.
Right? So look at this, right? So I never say T1 and T2 are different. There are any two tuples, they could be the same one, right? Make sense?
Yes,
yeah.
It does.
So if you have a relation with only one tuple, right? So then there's only one possible assignment of T1 and T2, which is that tuple. And you can actually find T3 and T4, which is that tuple, right?
Sure, that makes sense. Okay, fair.
Makes sense, right? Okay, cool. Yeah. Perfect. Okay, so let's continue. Okay, so now let's look at this example, right? So you have person number, you have language, you have programming language. So there's actually MVD from person number to language. There is MVD from person number to programming. Okay, so why? Because you can actually go back to the definition, right? So essentially the language and programming language, they are conditionally dependent on personnel number, which means that if I have, okay, so if I find any two tuples, for example, the first one and the second one, right? So I can always find another tuple that takes the first value Greek from the first tuple and take the second value from the second tuple Pascal, right? So essentially, language and programming language are kind of conditionally independent, right? So we have MVD here. Similar to functional dependency, MVD can result in anomalies and redundancies, right? As you can see, because there are redundancies, right? What if someone speaks a new language, right? Someone learn like English, right? So 3002 learn English. You need to insert multiple tuples into the relation because you also need to consider all the programming language that person knows, right? So that is actually the source of anomalies that can be caused by multi-value dependency. Another way to think about MVD is to think about that in terms of joins. Okay, so essentially, if you give me a relation alpha, beta, gamma, and if there is a multi-value dependency from alpha to beta, it pretty much means that I can have a lossless decomposition of R into R1 and R2, in which R1 takes alpha and beta, R2 takes alpha and gamma, and R is the join of R1 and R2. Okay, so in this case, you could have one relation contain personal number and language, right? 3002 will Greek Latin in that relation. You can have another relation with personal number and programming. 3002 will have C and Pascal, right? When you join them, you get your skills table, right? When we say there's a MVD from alpha to beta, essentially we mean that R can be decomposed in this way. And by doing join is actually another way for us to express this type of conditionally independency between multiple attributes. right? So in fact, right, so the decomposition of R into R1 and R2 is lossless if you either have there's MVD from alpha to beta, or you have there's MVD from alpha to gamma. Okay. Yeah. So similar to functional dependency, when we are talking about the multi-value dependency, we can also have a redundant system, right? So it's not the Armstrong axiom anymore. You can have a different set of infinite rules using which you can kind of derive multi-value dependency, right? So there's a relationship between different type of multi-value dependency. For example, if you have alpha to beta, you always have alpha to gamma, right? So that is something we are going to talk about in the next lecture. And then given multi-value dependency, you can also define, for example, another type of normal forms, which is very similar how we define that for functional dependency that help us to get rid of data redundancies caused by a multi-value dependency. Okay, so that's first normal form. That's something we are going to talk about in the next lecture. Okay, so that's all for today. We are 18 minutes earlier. Well, any questions, just speak up. Yeah.
Mr. Zhang, there was a question in chat. What if there are more than 3 columns? And people want me to ask that.
Oh, okay. Yeah, sorry. Yeah, alpha, beta, each of them are a subset of attributes. Does that make sense? So essentially, you say.
Can you repeat that?
So here, alpha and beta, like alpha, beta, gamma, they are not a single attribute. There are 3 subsets of attributes.
Oh, okay. I think that makes sense.
Yeah. So like when we write alpha, beta, gamma, right? So that always means a subset of attributes. When we write ABC, and that's a single attribute. Yeah. And here essentially you say, okay, so you give me a relation. I don't care how many columns you have. I can decompose. So I can partition it into 3 different subsets: alpha, beta, gamma, and then I read them in the level of subsets instead of each specific attribute. Make sense?
Yes, I think it does. Thank you very much.
Yeah, perfect. Yeah, perfect. Okay, perfect. Yeah, if you have any questions, just let me know. Otherwise, I'll see you guys on Wednesday. Yeah. Oh, by the way, so the recording for the last lecture will be uploaded over the weekend because I have to redo that. Somehow I forget to click the button last Wednesday. Yeah.